Hello, my name is Jacob Swindell, and this is my DigiCrop 2025 presentation on discrete representations for Gaussian process weed maps. So, farmers want maps of their fields because they assist in daily operations and decision making. In the case of our work, we focus on weed maps. If a farmer had a map of all the weeds in their fields, they'd be able to use precision agriculture techniques such as precision spraying in order to target the weeds and not damage the rest of their fields. In order to produce these maps through manual surveying, would be very time consuming and costly. So we'd want to automate the process. The most common way of doing this is through the use of UAVs in order to scan and produce maps of a field quickly. So the industry standard way that UAVs would produce these maps is through orthomosaics. So these are made from the UAV flying over the field and taking images with large overlap and then stitching these images together offline in order to produce a very large high-resolution map of the field. This is very accurate, but has some sort of specific downsides. One of these being that the UAV has to fly in a very specific pattern in order to cover the whole field. And another downside being that the operation is often very time-consuming due to the high-resolution images and the rectification and image processing that has to be done to the images in order to stitch them together. So this process can take a very long time and has to be performed offline, can't be performed online on the drone. So as an alternative to this approach, you could use 2D Gaussian process mapping. So a Gaussian process is a probability distribution over a set of functions. In the case of spatial data, it would be 2D functions. And how it works is that you use a variogram, which defines the spread of the data, and then you train the GP on samples with a position and a value, the value being the variable that you're trying to map across the field. In this case, it would be weeds. This produces a continuous representation of that variable across an area. So in order to view this, it has to be discretized into mean and covariance. So you can sample from the GP once. If you wanted to produce a map of the field, you'd have to sample and produce a representation. So the two most common methods is grid map and quad trees. A grid map is very simple. You just sample at a fixed distance across the whole field, and then you produce an image. A slightly better approach would be a quad tree, which is able to represent areas that are very similar in large blocks and areas with lots of detail in sort of smaller pixels, whereas a grid map is the same resolution throughout. So quad trees save a lot on the resolution of the map. If you look at works that use Gaussian process mapping, you'll see that they will mainly use grid maps and quad trees. But if you look at a field like computer vision, you can see that many more representations exist, and it's understood that different representations will be able to represent an image better compared to others. Better meaning that it might be more accurate, it might be faster to compute, it might compress more memory but lose less data. And so the purpose of this project will be to test these representations taken from computer vision and see if there's any benefits to be had in the field of Gaussian process mapping, because maybe these representations might be an improvement over grid maps and quad trees that we haven't seen. So the representations we chose to test in this work were wedgelets, binary space partitioning tree, and hexagon maps using the UberH3 library. So wedgelets is a variation on quad trees, and the binary space partitioning tree partitions the image into a binary tree. This is either with a bottom-up approach using the Kruskal algorithm or a top-down approach which recursively divides the image. These representations are compared against quad trees and grid maps in order to evaluate their effectiveness. So in order to produce the 2D Gaussian process for testing the representations, we used a orthomosaic from the weed map dataset, which has already been referenced in this presentation. And then we used random sampling with average pooling in order to train a GP using the exponential variogram. So after implementing the algorithms for the representations and applying them to the Gaussian process, we produced these maps. As you can see, the grid map is the highest resolution that we have. Quad tree and wedgelets look roughly the same, but can clearly be lower resolution than the grid map. Comparing the two binary space partitioning representations, we can see that both represent the areas of high interest with more dividing regions, which is good, which is what we want. We want high detail in the areas which are interesting and low detail in the areas that are not interesting. Same can be said from the hexagon representation. There are lots of smaller hexagons on the areas where there's very high weed values, and there's larger hexagons in the areas where there's not. So all in all, these representations are working correctly for the GP. So to evaluate these representations, we use 3 different metrics. We use structural similarity, Hamming distance, and mean squared error. So structural similarity and Hamming distance try and mimic the way a human eye would measure the similarity between 2 images. And for these 2 metrics, the quad tree is best for every single map type. However, when we look at mean squared error, which is a pixel by pixel comparison of how accurate the representations are, we can start to see more interesting results. So depending on the orthomosaic, different representations are actually the best. If we average across all orthomosaic types and all distributions, then the binary space partitioning tree, the least squared error, so the top-down partitioning, actually performs very slightly the best. However, the quad tree and the wedgelet is still very competitive. For the time and space metrics, the fastest to compute is the binary space partitioning tree region approach, and the one that takes up the less space in memory is the hexagon map. But the binary space partitioning tree, the least squared error, also is a very respectable memory reduction when compared to the quad tree and the wedgelet. So in conclusion, the purpose of this project was to prove that quad trees are not necessarily the best representation to use for all distributions for Gaussian process mapping. We've shown that depending on the map type and the distribution, that different representations can actually perform the best, and more work needs to be done in this area to evaluate different representations depending on the distribution. We've also introduced binary space partitioning tree as a potential general use representation that performs well across many different map types and distributions. For future work, we'd like to evaluate what types of distributions indicate that a certain representation would be better suited to it. So that's the end of my presentation, and thank you for listening.